Hello students, it's Dr. Sansom here, and we're ready to do our lecture on chelation. So, we have a quote today from Albert Einstein: try not to become a man or woman of success, but rather try to become a man or woman of value. And I love this. I think as you're getting your education at BYU and going on to do great things in the world, keeping this in mind, how you can contribute, how you can make the world a better place, is always the right choice. So today we're going to be talking about coordinate covalent bonding in ligand metal interactions in these coordination compounds. We're also going to talk about factors that affect binding strength and the values of Kf for complex ions, and calculate the coordination number, oxidation state, and charge of a complex ion. Those are pretty easy things to do at the end. So let's begin. If we think about a cation in water, we see something written like cobalt 2+, and we put this AQ after it. So what does that mean? It means that their cobalt ion is dissolved in water. And how exactly is the cobalt going to interact with the water? Well, it has a positive 2 charge, and because of that, water, which is polar, will orient itself in a way so that the partially negatively charged oxygen atoms will point toward the positive charge on the metal ion. And in general, an ion that's dissolved in water generally will have several water molecules that are associated with it. So this is actually a kind of image or picture of what we can imagine, that we have our 2+ ion here, and then the water molecules are all oriented toward it. And in this diagram, we've also drawn in things that look like bonds. Those are actually coordinate covalent bonds, so we'll talk about what that means and what that looks like here in just a minute. Molecules besides water can do the same type of behavior. They just need a lone pair. If they have a lone pair of electrons, then they can bond to these transition metal ions. And these particular types of bond are called a coordinate covalent bond. Unlike a regular covalent bond where you'd have like one electron from carbon and one electron from hydrogen, and then they end up sharing the 2 electrons, in a coordinate covalent bond, the metal ion doesn't have any electrons, no valence electrons, to share in that bond. And so both of the electrons for the bond come from the ligand, which is essentially that lone pair on the water molecule or the other ligand molecule. There's lots of examples of things that do this. Cyanide, chloride, and ammonia are common examples. What do you think? Are these going to be Lewis acids or Lewis bases if they're donating their electrons to make this bond? That's right, they're going to be Lewis bases because they're donating the electron and making that new bond. So an example here with our cobalt that we started with, we can have it just aqueous, bonded to these 6 water molecules, but if we add chloride ions, they can also act as ligands and make this tetrachlorocobalt compound over here. Now, in this example, it should be pointed out these have very different properties. In fact, our cobalt solution in just water is going to be pink, but when we add the chloride, it turns blue. So it'll have a totally different electronic structure because of that ligand. I just want to draw out what this looks like for a coordinate covalent bond. So I'm going to have my cobalt ion here, cobalt 2+. It doesn't have any valence electrons, but if I have something like water, it has these extra lone pairs of electrons. These 2 electrons are going to be donating to the cobalt, and then we get our new cobalt metal ligand bond. And of course, there's another lone pair on that oxygen as well. But this is our new bond that we formed as a result of that ligand metal interaction. We call it a coordinate covalent bond. To distinguish it from the regular type where you'd have like a carbon with one electron and a hydrogen with one electron, and then they end up making a bond where they're sharing 2 electrons, that's different than what we're seeing here, because here both electrons come from our donor. Okay, so now what are some of these ligands? Here are examples of common ligands: ammonia, water, hydroxide, cyanide. And notice we're highlighting here that they have those lone pairs. And this is super important because in order to make this type of bond where both of the electrons are coming from the ligand, they have to have a lone pair to do that. So a coordination compound is what it's called when the ligands bind to the metal cation using this special type of covalent bond called a coordinate covalent bond. And sometimes coordination compounds are also ionic. They have a charge overall, and then we would call them a complex ion. And here are some examples. This copper with ammonia is a classic example. You guys actually are going to make this in Chem 107 in your experiment 10. FeH2O6 3+ is a classic example as well. And you already made FeSCN2+, that's a coordination compound as well, and you made that in your equilibrium experiment, that deep red color. So in this case, we have the central metal ion, and then we have these other molecules that are surrounding it and making that coordinate covalent bond. We call those ligands. Sometimes people say ligand, and that's fine. Ligand or ligand. The word is from Latin and it means to bind. So here are some examples. All of these are compounds that are formed with nickel ions and then different types of ligands: water, ammonia, and then ene, ethylene diamine. We'll talk about what that is in a minute. But notice, as I go from water to ammonia, what's true about my ability to donate electrons? Well, water has oxygen with alone pairs, which is pretty electronegative, so it's harder for it to donate electrons, whereas ammonia is better able to donate electrons because it's less electronegative. And so that actually forms a stronger bond. It forms a stronger bond, and that's reflected here in the color of light that it absorbs, or the wavelength, or the energy. It's a higher energy bond because it's stronger, because this one is better able to donate electrons. What about comparing NH3 versus ethylene diamine? Now, you don't know what that is, but it has nitrogen in it, and it also has a bunch of carbons around. So if you remember from our unit on acids and bases, we know that's going to increase the strength of that lone pair and let it donate more electrons, making an even stronger bond. And that's again reflected here in the color of light that it absorbs, being a higher energy wavelength of light. There are a bunch of ligands that you should be aware of. All of these monodentate ligands. Monodentate just means they form one bond. Dentate is like tooth, so it has like one tooth where it's going to attach to that metal ion. Water, ammonia, fluoride, chloride, cyanide, thiocyanate, hydroxide, and nitrite are very common monodentate ligands. All of them have the same thing in common. They have these lone pairs of electrons, and many of them, most of them, also have a negative charge, which helps them donate those electrons. There are also bidentate ligands. That means that they can make 2 bonds to the metal ion. Ethylene diamine, or ene, is a classic example of this. So that's one that you should be familiar with. It's got an ethylene here, the CH2, and then diamine. There's an NH2 and an NH2 on either side. And these nitrogens have lone pairs that will make bonds with the metal ion. We can also have polydentate ligands. Diethylene triamine, or diene, is a common one that you'll see. It actually can make 3 bonds to the metal ion. And then ethylene diamine tetraacetate ion, or EDTA, is also a common one. This one is actually hexadentate, so it forms 6 bonds, one here at the nitrogen, another here at the nitrogen, and then one here at the oxygen on each of these 4 acetate groups. So if we have a ligand that can make more than one bond, like a bidentate or polydentate ligand, we also call it a chelating agent. Chelating comes from the Greek word for claw, and you can imagine these molecules just kind of wrapping themselves around our ion in the middle. This is a picture here on the left of ethylene diamine making the 2 bonds. Each molecule makes 2 bonds to that central ion. And so there's 3 molecules of ethylene diamine here on the left. On the right, this is actually showing EDTA, and that molecule being wrapped all around this metal ion, making 6 different bonds with that metal ion. So looking at a molecular level picture here, this is our ion with just water. When we add ammonia, it turns that deeper blue color, and then purple when we add the ethylene diamine. So now here's the question. If I have my nickel with water and I add ammonia, and then it makes NiNH3 2+, and releases 6 water molecules, the Kf for this reaction, which is our constant of formation, is 1.2 times 10 to the 9th. So that's pretty big. But I want to know, is it driven by enthalpy or entropy? And if I look instead at H2O down here, and now I'm replacing it with ene molecules, 3 ene molecules, notice there's a big difference in the size of Kf. Is this one driven by enthalpy or entropy? What's the difference here? Go ahead and talk about this in your groups if you have a group with you, or think about it on your own for a minute. I hope that you've had some time to think about this. You paused the video and thought about it. Let's look at this example, the first one. We've got water, and then we've got NH3. Now, we already talked about this. NH3 is a better base. It's better at donating its electrons, and that's because it has that lone pair on a less electronegative atom like nitrogen. And so what's going to happen here is I'm going to make stronger bonds. And when I make stronger bonds, that is an enthalpy issue. So this first reaction is driven by enthalpy. And in fact, if you look at the right and the left, we have the same number of free moving particles on the right and on the left, so there shouldn't be a large change in entropy here. There might be a small change in entropy, but this is going to be due, this large Kf, which drives this reaction forward, is mostly due to the stronger bonds that I'm able to form with the NH3. Looking at the bottom one, now we know that ene is a slightly better base than NH3, but both of them are with nitrogen, so this one might make slightly stronger bonds, but there's something else going on as well. That only really accounts for a small difference, but look at the value of our K. It's gigantic, 10 to the 17th. How does that happen? Well, if we look at the number of molecules on the left, we only have 4 molecules on the left. On the right, we have 7 molecules. So we are able to release 6 molecules of water when that chelating ligand, ethylene diamine or ene, binds to nickel. And because we have so many more free moving particles on the right, this is actually driven by entropy. And entropy, the chelation that results in releasing all of these molecules, is what drives this reaction and makes that Kf so much bigger than the Kf for just the ammonia. Chelation is actually super important in biological systems, and one classic example is heme, which you might be familiar with from hemoglobin, which of course is the protein that helps to transport oxygen in your blood. And when you have hemoglobin, you have the protein, there's a histamine here that takes up one spot, complexing with the iron, and then this molecule here that's called heme, that's the heme group, and that will take up 4 spots, and it leaves 1 spot left where oxygen can bind. And in fact, CO2 can also bind here. Both of those bind sort of weakly, and that's important because we want it to be affected by how much oxygen is around. If there's a ton of oxygen around, like in your lungs, you don't want the oxygen to come off of your protein. You want it to go to the place in your body, like your fingers, where there isn't a lot of oxygen. And then because there's not a lot of oxygen, the oxygen will come off of the protein, right? And be able to oxygenate your tissues. And where you have lots of CO2, like in your fingers, you want that CO2 to stick better to the protein and then get carried away to your lungs where you don't have as much CO2. Then it will come loose and you can exhale the CO2. So this idea of them having a kind of medium strength bond is very important to the way that this functions in our body. Now there's a couple of other things that are quite poisonous that will also bind to the iron here. Carbon monoxide and cyanide are examples. Cyanide binds about 1,000 times more strongly than oxygen, and carbon monoxide binds about 100,000 times more strongly. And because of that, they'll take up the spot on the hemoglobin, and oxygen can't stick to it, so you're not able to oxygenate your tissues. Now, this also shows up in plants, but in a slightly different way. Chlorophyll is actually chelating, and it will chelate around magnesium ions. And that might seem kind of weird, like why would we do that with magnesium? But remember, magnesium will precipitate with carbonate, which is very common because of like carbonate buffering. And so if we don't keep the magnesium chelated, basically preventing it from precipitating, then you'd get all of this buildup of white chalky stuff inside, which would not be good for the plant. It wouldn't be able to transport things around inside of the plant. Okay, so that's our introduction here to this idea of chelation, that it's like a claw. It can bind in multiple sites. And there's a few little details we've got to do now with describing the coordination compounds. So this next part is a little bit more practical and applied. Essentially, this is like a notation issue. So we use these square brackets. Now, normally when we see those, that indicates that we have a concentration that we're supposed to pay attention to, that those are molarity. But in the case of coordination compounds, the brackets just separate out all the stuff that's connected to the metal ion from anything else that's there. Okay, so in this first example, CO NH3 we know there's 6 NH3s that are connected to the CO, and these Cls that are here on the outside, those are just counter ions. So this whole complex ion must have a +3 charge, and the chloride is there with the minus charge to balance that out. Okay, and you can see different examples here, things going into and out of the parentheses. Sometimes our counter ions are positively charged because our complex ion is negatively charged, and that's okay too. But we have some rules for how we're doing this. Inside of the brackets, we list first the central atom and then all of the ligands. And if we have counter ions there, we don't always, because it could be a neutral coordination compound, but if we have counter ions, the cation always comes before the coordination compound, or if it's an anion, it comes after. Whenever you have any compound, it's always cation and then anion. So that's true here with our cobalt, and it's also true here with the sodium and the platinum, that the sodium is positively charged, so it comes first. So 3 different things that we're going to talk about now. The first is coordination number, and coordination number is the number of metal to ligand bonds in a coordination compound. It's important to note this is not the same as the number of ligands, because remember, some ligands can make multiple bonds. Counter ions are not part of the coordination sphere, the ones that are actually attached to the metal. They're just balancing the charge in the salt. The coordination number is going to depend on the size of the metal and the size of the ligands. As an example, iron 3 ions can bind 6 fluorides, but only 4 chlorides because of the size issue. So pause the video here and write down what you think the coordination number is for each of the following compounds. Okay, looking at this first one, I've got my cobalt, I have 3 ammonias and 3 chlorides, so I think the coordination number for this is going to be 6. In the second one, I have 6 NH3s here and I have 3 chlorides, but notice the chlorides are outside of the bracket, so my coordination number here is also going to be 6. For this one, I've got platinum, NH3, and then Cl3. That looks like 4 things connected to the platinum. And finally, I've got NH3 2. That's just 2 things connected to the platinum. So let's have a quick poll. What is the coordination number for this guy? Hopefully you came up with 6 because that's the correct answer here. 5 NH3s and 1 Cl that are bound to the cobalt. So that's the first thing, is the coordination number. Second thing that we're going to talk about is the charge on the complex ion. So here we want to know what's the charge on just the complex ion. So we're going to look at the counter ions to figure that out. So in this case, I have 3 chlorides. I know chlorides are always -1. And so our compound, our complex ion, must have a +3 charge. What about this one? Here I've got 1 sodium ion. Sodium is +1, and so our complex ion must have a -1 charge. What about this guy with rhenium? What should our charge on the complex ion be? The correct answer here is 2, because I have 2 nitrates. Nitrate has a -1 charge, so my complex ion must have a +2 charge. Okay. Now, this is on your worksheet. Again, if you're with your group, you can do this with your group, or you can pause the video here and answer these questions. But I want to know, what is the oxidation state of platinum in this compound? One way to figure this out is that our metal oxidation state, or charge, it's the same as the charge, is equal to the complex ion minus the charge on the ligands. So if I know my charge on my complex ion, which I just figured out, and then I can subtract out the charge on the ligands if they have any charge, then that'll give me my charge or oxidation state on the metal. In this case, because our metal is always just by itself, the charge and the oxidation state are the same thing, but we normally call it the oxidation state. So in this case, I have -2, which is my charge on my complex ion, and then I'm going to subtract out the charge on my chlorides, which is 4 times -1. So I come up with +2. So my oxidation state on platinum is +2. Go ahead and pause the video here and answer this for the other 3 questions. So our oxidation states here in the first one, I've got the metal equals my complex ion, which is +3, minus the charge on my ligands, which is 0 because NH3 doesn't have any charge. So I must have a +3 oxidation state for my metal. Here for platinum, I know that my whole ion is -1, and then I'm going to subtract the charges on these. The ammonia is neutral, but chloride is -1. So I'm going to subtract -3, so I come up with +2 for my oxidation state. And then for silver, the whole thing is +1, my NH3 is neutral, so I end up with a +1 for my oxidation state. Quick quiz for you, what's the oxidation state of nickel in this compound? I know that the overall complex ion has a -3 charge because it took 3 potassiums to balance it out. And I know that cyanide is a -1 charge, and I have 5 of those. So I'm going to have -3 minus -5. That gives me +2 for my oxidation state. Okay, last thing. What properties are going to govern a ligand's ability to make a strong or stable coordinate covalent bond with a metal ion? Here, the biggest thing is whether it can act as a Lewis base. In order to make that covalent bond, the coordinate covalent bond, it has to be able to donate a lone pair. So things that are more basic are going to be better at donating that lone pair. For example, we saw ammonia was better than water, and ene was better than ammonia. Second question, what properties make the ligand entropically favorable in a complex formation? If entropy is the thing that we care about, then that's always going to be related to chelation. If I have a ligand that can take up multiple spots on that metal ion to make multiple bonds to the metal ion, then that ligand is going to release the water molecules or whatever other monodentate ligand we might have had around. And that is a hugely favorable thing for entropy because we have more free moving particles at the end. So looking for polydentate ligands is going to be the key thing to if we're caring about entropy. Last thing, how do we calculate coordination number, oxidation state, and charge on the complex ion? The coordination number, we're just going to look at the ligands that are in the coordination sphere, and we're going to count them up and make sure to take into account if we have any bidentate or polydentate ligands. Like if I had ene, that would count for 2 bonds because it makes 2 bonds. Oxidation state of the metal ion, I'm going to calculate by looking at the charge of the overall complex ion and then subtracting out the charge of any of the ligands. That'll give me the oxidation state or charge on the on the metal ion. To get the charge on the complex ion, I just look for the counter ions and how those play out. Okay, that's everything for today. Thanks for listening, and I hope this is helpful, and I will see you next time.